Hello, my name is Guilherme and I'm going to present the work Numerical Investigation of the Destructive Interference of two Nonlinear Standing Waves in a Duct by myself and Professors Roberto Mizerdi and Adriano Fabro from the Department of Mechanical Engineering at the University of Brasília. The objectives of this work are to investigate the influence of nonlinear effects on the shape of sound waves and, more specifically, the influence of those effects on the interaction of standing waves with opposing phases. It is possible to divide the nonlinear effects into two groups. The first is associated with the large amplitude of the waves that causes a change in the speed of sound and the advective transport of the wave by the flow induced by the passage of the sound wave. The other group is the effect of the thermodynamic reversibilities that include viscous effects and heat transfer. In this work, sound waves are generated by the oscillatory movement of walls at the extremities of a one-dimensional duct. And this work is divided into 4 parts that aim to investigate different aspects of the influence of the nonlinear effects. The first part is the study of plane waves that propagate in a duct with an open extremity. The second case is the study of standing waves formed in a closed duct when the length of the duct is a multiple of the wavelength of the sound. The third case is the study of the interaction of standing waves with opposing phases. And the final case that I will not cover in this presentation is the study of the continuous interaction of sound waves in a closed loop. For our cases, the frequency of the sound waves was chosen to be 1000 Hz. In this work, we chose to model the fluid flow by the Euler equations for compressible flow. And this means that only the nonlinear effects associated with the large amplitude are captured, and those associated with viscosity and heat transfer are disregarded. Those equations are solved with a moving body immersed boundary method that includes a finite volumes domain discretization with a fourth-order interpolation scheme to calculate the fluxes, and a third-order von Schütte scheme for the time march. And this method is presented in detail by Mizerdi et al. In this paper. During the study, we noticed that because the amplitude of the movement of the walls necessary to generate sound waves is very small, the boundary remains at the same control volume for several time steps. And because the original immersed boundary method only considers the average values inside the control volumes to calculate the boundary conditions, we noticed that this movement would not influence the flow. So we decided to apply a linear interpolation scheme inside the control volume based on this distance delta from the left side of the control volume to the position of the boundary. And with this, we expect that we'll be able to better capture the movement of the walls and its influence in the fluid flow. These figures show the pressure as a function of time for plane waves that propagate inside an open duct. The figure on the left shows the case of an approximately linear wave with a small amplitude. It's possible to see that there is no significant change in the shape of the wave as the wave propagates. The figure on the right, on the other hand, shows that because the amplitude of the pressure fluctuations is very high, there is a significant change in the shape of the wave caused by nonlinear effects, and the wave eventually acquires this sawtooth shape with discontinuities at the extremities. This figure shows clearly how the nonlinear effects influence the shape of the wave. Because the velocity of propagation is higher in the compression regions and smaller in the expansion regions, and the induced flow is in the same direction of the propagation of the wave in the compression region, and in the opposite direction in the expansion region, the distance between the peaks and the valleys increases with time. This video shows how the standing waves are formed in the simulations. The sound waves are generated by the oscillatory movement of a wall on the left side, and they are reflected by a wall on the right side, and the interaction of those waves propagating in different directions generates the standing wave. For the approximately linear case, the amplitude of the movement of the walls is 10 to the negative 8 meters, which corresponds to an original sound wave with a sound pressure level of 57 decibels. And in this approximately linear case, it's not possible to observe any significant changes in the shape of the standing wave with time, even for longer simulation times. For the case of the nonlinear standing waves, on the other hand, with associated to a wall movement amplitude of 10 to the negative 4 meters, and an original sound wave with a sound pressure level of 154 decibels, we can see that as time passes, there is a significant change in the shape of the wave even for short periods of time. As time passes even more, there begins to appear a region with a very high pressure gradient that eventually becomes shock waves, as we can see in this figure on the right. This figure shows the average sound pressure level inside the duct for the case of the plane waves propagating in an open duct for this curve with the circles, and for the case of an interaction of standing waves with opposing phases in this curve with the squares. This interaction of the standing waves with opposing phases should result in a completely destructive interference if there were no nonlinear effects. And this figure shows that up until an amplitude of 10 to the negative 6, the two curves are approximately parallel, and there is a consistent reduction of about 40 decibels after the interaction of the standing waves. But as the intensity of sound increases, those two curves get closer together, which indicates that there is a smaller reduction in sound pressure level due to the interaction of standing waves. This video shows how the sound waves with a very small amplitude for the approximately linear case interact inside the duct to generate two standing waves with opposing phases that interact with each other, resulting in a destructive interference. It's possible to observe from these graphics of pressure as a function of time for the interaction of approximately linear standing waves that after the complete interaction, there is some residual pressure fluctuation, which indicates that even in this case, there is an influence of the nonlinear effects. This video, on the other hand, shows the interaction of these sound waves with a very high amplitude, associated to the nonlinear standing waves. It's possible to observe after the complete interaction of the standing waves that there is a significant amount of pressure fluctuations remaining. It's also possible to observe this from the graphics of pressure as a function of time, which indicate that even after the destructive interference, there is a significant amount of pressure fluctuations, which indicates that in this case, the nonlinear effects are very significant. These results indicate that the nonlinear effects associated with the high amplitude of the sound waves were properly captured by the numerical simulations of the Euler equations for a compressible flow. And it was also possible to observe that the influence of the nonlinear effects depends both on the intensity of the sound waves and on the distance from the source of the sound. The results for the linear standing wave were compatible with the expectations from the linear acoustic theory, and the results for the nonlinear standing waves were also compatible with the expectations from the nonlinear acoustic theory. The results for the interaction of standing waves with opposing phases showed that for small amplitudes there is mostly destructive interference, which indicates that in these cases the nonlinear effects are not very relevant for the study. However, the results also indicate that even for small amplitudes, there are some nonlinear effects, which is compatible with the theory for waves in non-dispersive medium. These are the references used in the presentation, and this is the paper with the description of the numerical method. Thank you.